Hi everybody. Hope you had a fun Halloween. I had about 6 trick-or-treaters at my house, but that means I have a lot of candy left over, so that's fun. The President Taylor, he spoke in here on yesterday, I think. So they use this. This is not on right now, so don't worry about it. I'm just gonna do my best not to run into it. Okay, so some announcements. Our Chapter 6 Achieve homework is due Monday as always. My office hour today is at 2 p.m. If you want to stop by, my door will be open upstairs. The Chapter 5 Learning Curve, so we finished Chapter 5 last week. The Learning Curve is available, the extra credit assignment, it's on Achieve. It's due November 19th, so you can work on it now. November 19th is about 2 days after our next exam. So, yeah, go ahead. No, because Chapter 4 was on the midterm. So yeah, so our next exam will be not cumulative. It'll be Chapters 5, 6, and 7, I believe. Definitely 7. I don't think we'll get to 8 before it. Our final is cumulative, so our final will cover all the chapters that we've covered this semester. And then also, so I know we're a little bit past halfway through the semester, but each semester I like to send out a survey to all of my students. So everyone in my 2 Chem 1070 sections are going to get this survey. And this survey is a place for you all to give feedback to me on the course structure, on just everything that is involved in our class. So I find your feedback very valuable. I'm going to read through everything and we'll talk through some of what you all said together in class. But my main goal in general is for you all to learn chemistry and to enjoy learning chemistry. So as you're filling out the survey, and it says this at the beginning, really focus on providing constructive feedback for your learning. So I know you might not enjoy everything that we do in the class, but if it's helpful to your learning, then that's important to me. That's what I want to know about. So keep that in mind. I'll send out that survey link via a Blackboard announcement today. Just like we give you all midterm grades, this is like somewhat of a midterm grade from you all, but to me. So we will continue on with our Chapter 6 thermochemistry notes. On Monday, the last thing we did was this learning check, where we were calculating the amount of work performed during a reaction. This reaction was in a sealed flask with a piston. And if you remember, this is what that setup looks like, where we have a flask that's closed off to the atmosphere and then sealed with a piston as well, so we can determine if any work is occurring. But most of the time when you are doing a chemistry experiment in a lab, you have an open beaker, it's open to the atmosphere, pressure remains constant. And so that's what we'll focus on here, where most chemical reactions that are performed in general are in open systems where both heat and work and matter can be exchanged from the system to the surroundings or from the surroundings to the system. And so chemists are most often interested in the flow of heat specifically at a constant pressure. So if we have an open system, that system is exposed to atmospheric pressure, 1 atm. That's not changing. Our atmospheric pressure is not going to change. So we'll generate equations related or using that definition of pressure at constant pressure. And so enthalpy is what we'll talk about here. Enthalpy is another state function, so it doesn't matter what path you take to change enthalpy. And it relates the internal energy, so U is our internal energy, pressure is P, and volume is V. So this is the equation for enthalpy. Internal energy plus pressure times volume. And then we will take this equation, I'm going to rewrite it up here. So this is our definition of enthalpy from the previous slide. If we're looking for change in enthalpy, but at a constant pressure, then we represent that with a delta H, change in enthalpy, is equal to the change in internal energy, delta U, times P. Pressure is not changing, so we don't need a delta for P, and then delta V for volume. Volume can change. So this is up top is the definition of enthalpy. The second equation on here is how we define enthalpy change. So if enthalpy is changing, we put in those deltas. Well, from previous equations, we saw that delta U, the change in internal energy, is equal to the heat exchange plus the work change. So if we're saying this is occurring at constant pressure, that's what this represents here. Flow of heat, which is Q, at constant pressure, which is that subscript P. So delta H is equal to flow of heat, Q, at a constant pressure, plus work, plus pressure times change in volume. But we've also seen in previous slides that work is equal to negative pressure times change in volume. So if we substitute now pressure times change in volume for this equation, we got a negative W here. So now we have change in enthalpy is equal to change in internal energy plus W minus W. We can cancel out the W's, and we have change in enthalpy is equal to the change or the flow of heat, Q, at constant pressure. So we will certainly use this equation when we're calculating enthalpy change for processes. So change in enthalpy is equal to the flow of heat at a constant pressure. Pressure is changing, we need a different equation. We can describe enthalpy very similar to how we've described the flow of heat, where if enthalpy is greater than 0, if change in enthalpy is greater than 0, that means our heat flow is greater than 0. It's a positive number. This means heat is transferred from the system to the surroundings. I'm sorry, from the surroundings to the system. I mixed that up. Delta H is greater than 0. Heat is transferred from the surroundings to the system. So the system is absorbing heat. So this we defined as an endothermic reaction or endothermic process. If the change in enthalpy, delta H, is less than 0, that means we have a negative value for Q, negative value for delta H. This occurs when heat is transferred from the systems to the surroundings. So the surroundings lose energy. I keep mixing this up. The surroundings are gaining energy. The system is losing heat. So reactions that transfer heat to the surroundings are known as the exothermic. Okay, so let's do this learning check. This one will be an iClicker. So we have wood burned in an open fireplace. We've seen this example before. So this is an open system. Nothing is closed off to the atmosphere. So that means the reaction occurs at a constant atmospheric pressure of 1 atm. The reaction releases 250 kilojoules of heat and does 15 kilojoules of work on the surroundings. So each of these will be a separate iClicker. So determine if the reaction is endo or exothermic, calculate change in enthalpy, and then calculate change in internal energy. And then if you have questions, please let me know. I can get this going.
What's a bomb calorie? Are you just like think about this is only true when the reaction is in this case.
That's atmosphere. These are things that atmosphere is 1.35. No. I am. I was taking another year, but now I'm
Say 1 more minute.
We said that 8 years. That's what
Okay, about 10 seconds. Try to get at least one answer submitted. All right, I'm gonna end it here. Oops. Let's see what we're thinking. All right. About the same as earlier. Pretty good mix for this last question here. So let's regroup for this question. We have wood burning in a fireplace. If you think conceptually about what happens when you burn wood in a fireplace or in a fire pit, we do that to produce heat. So that wood burning is releasing heat into the surroundings. We can experience that if we're near the wood burning. The statement also says that this reaction releases 250 kilojoules of heat. So the system is releasing heat. That means that it's an exothermic reaction. Heat is being released. And then we are asked to calculate delta H. So we'll use the equation we have on the previous slide. Delta H is equal to the heat flow at a constant pressure. When you have an open system, like an open fireplace, the pressure is constant. We have 1 atmosphere of pressure. And so our delta H, our change in enthalpy, is just equal to the amount of heat released or absorbed. In this case, the system releases heat, so our Q value is negative, and it's releasing 250 kilojoules, so delta H is negative 250 kilojoules. Yes.
So if it absorbs, that'd be positive 250.
Yes. Yeah. So if it said like the reaction requires 250 kilojoules of heat, or the surroundings lost 250 kilojoules of heat, then it would be positive. And then our last part C, we're calculating delta U. This is change in internal energy. We defined this on Monday, and the equation is on the 2 slides ago. So this one right here. Delta U is equal to heat flow plus work. In this case, the heat flow for the reaction is the heat is being released, so we have negative Q. Same value, same concept as the last question, part B. And then for work, the statement says 15 kilojoules of work is done on the surroundings. So the system is doing the work. The work is done by the system on the surroundings. So that means our work value is also negative. So we have our Q value, negative 250 kilojoules, plus negative 15.0 kilojoules. Or if we simplify that, negative 250 minus 15. And so our delta U, change in internal energy, is negative 265 kilojoules. Another way to conceptually think about this, the wood is burning in the fireplace it's releasing energy. The internal energy, delta U, describes the energy of the system. So if the system is losing heat, then as long as it's not gaining a bunch of work, then delta U will also be negative because it's losing internal energy. Questions on this? Okay, so questions like this and the questions we've done in the past, we're calculating the flow of heat or change in enthalpy or change in internal energy of a system with some amount of a substance. So we didn't know exactly how much wood was present here that was burned in the fireplace, but we know it's some amount. If we have a large amount of wood present, then it will release a lot of energy. If we have a small amount of wood that's being burnt, then we will have less energy that is released. In chemistry, we can quantify the amount of energy released or absorbed for a 1 gram amount of a substance when it changes in temperature by 1 degree. And that's what we call specific heat. So this is our next section here. We're talking about heat required to change the temperature of a substance when we're talking about a specific amount of the substance by a specific temperature. So in the absence of phase change, which means we're not going from liquid to solid or solid to liquid or liquid to gas or gas to liquid, all we're doing is taking, for example, liquid water and increasing its temperature. The amount of heat required to change the temperature of a substance is given by this equation. So any substance, we can use that equation, any pure substance. where M is the mass, C is the specific heat, which we'll define, and then delta T is the change in temperature. The change in tongue twister, not really, I'm just struggling. The change in temperature has to be in Celsius or Kelvin. That is how we define specific heat, is through degrees Celsius. Fahrenheit will not work here. Yeah.
For questions with pressure, does it have to be like atmospheric pressure to work in an equation?
If it's an open system, then we would say it's atmospheric pressure. But if it's a closed system, they might define the pressure. So the specific heat, this is a property of substances. A different number of specific heat, a different value of specific heat is exhibited by different substances. But this is the number of calories or joules. Actually, don't know why that says calories. Most of these are defined as a joule. But remember, joules and calories are units for energy. So it's number of joules required to raise exactly 1 gram of a substance by exactly 1 degree Celsius. So I have some specific heat values listed on this next slide. Specific heat values are for a pure substance, so a atom, an element, or a compound. So we have metallic elements here, and then we have some covalent compounds or molecules over here as well. So they're, on this slide, they're all in units of joules per gram degree Celsius. So for 1 gram of carbon dioxide, that's our first molecule, the top left, to raise 1 gram of carbon dioxide by 1 degree Celsius, 0.852 joules of energy are required to do that. So we see we have different specific heat values. For example, water has a pretty high specific heat compared to others. Hydrogen gas has a pretty high specific heat. Metals have relatively lower specific heat. They're all less than 1. And so we can kind of conceptually understand this, where substances with higher specific heat values resist temperature changes more so than substances with lower specific heat values. So if we look at our previous slide, if we think of metals like aluminum, copper, a lot of these are used in cookware. It doesn't require a lot of energy. We have low specific heats. It doesn't require a lot of energy to increase the temperature of these metals. That's why they're useful in cookware. When you put them into the oven, they'll raise in temperature pretty quickly. But something like water, cookware example doesn't track here because this is liquid water now, but something like water has a higher specific heat. So if you have a sample of water, it requires a lot more energy to raise the temperature of that water. So I think the examples on this next slide, one is water. So just that water has a higher specific heat compared to the other substances. So water can absorb a significant amount of heat without experiencing a change in temperature. And then another example is dry sand. So you may have gone to a beach before on a really hot day, the sun is shining. The sand might be too hot to walk on with bare feet. Sand is mostly made of silicon dioxide, which has a specific heat of 1 joule per gram degree Celsius. And so that will heat up a lot quicker than the same amount of water that's present. I'm going to skip this slide. We'll come back to it. I just want to go through the next 2 slides first, because I think they make more sense to go here first. So molar heat, specific heat capacity. This is the same concept, except instead of joules per gram degree Celsius, we have joules per mole degree Celsius. So the molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. So the dependence of the change in temperature is on the identity of the material. Trying to understand what I wrote here. The dependence of delta T, so how much the substance can change in temperature, depends on the identity of the material, and that's expressed by the molar heat capacity. So same thing as heat capacity, but in this case, we're talking about moles of a substance. And then we can use the same equation, but in this case, we have N C delta T. We use N to represent number of moles. And then C would have to be the molar heat capacity. In units of joule per mole degree Celsius. And then delta T is still the change in temperature, and Q is the heat flow. So you might have questions where you need to use a molar heat capacity. You might have questions where you need to use the heat capacity per gram. If you, for example, are given the moles of a substance and the heat capacity in joules per gram degree Celsius, as long as you know what the substance is, you can convert moles to grams, and then you'll be able to complete the equation. So this next slide just has some molar heat capacity values you can use as a reference. Sometimes when we're doing these types of questions that involve heat capacities, we will use the change in temperature of surroundings to indicate the change, the change in temperature of the surroundings to indicate the heat flow from the system to the surroundings. And that gives us information about the system. So now we can go back to the slide before molar heat capacity. So signs can be used to indicate the direction of heat flow, or if you have a negative Q, that indicates the release of energy. So if we have a heated block of metal, drop it into a beaker of cold water, the hot metal and the cold water will exchange heat until they reach the same temperature, so the same energy. The heat will flow from the metal to the water. So all of the heat that's gained by the water is equal to the heat that's lost by the metal. And that's how we get this equation here. The amount of heat flow is the same for both the water and the metal, but the sign is different because one is losing heat, one is gaining heat. We can write this more generally, where Q of the surroundings is equal to negative Q of the system. Okay, we're going to do some examples, but before we go through those, anything that you all have questions about? Anything unclear at this point? Yes. Yeah. Just the concept of what that means? Oh, okay, so it's the same idea as the other heat capacities on the previous slide. It's just that, like, for example, for sodium as a solid, to increase 1 mole of sodium in temperature by 1 degree, you need 28.24 joules. So just the amount of heat required to change 1 mole of a substance by 1 degree. No, yeah, no. These, well, you don't have to memorize any of the heat capacities. They will be given to you. However, we will be using the heat capacity for liquid water a lot, 4.184. It's not a bad one to commit to memory, so you don't have to look it up every time. You might just get used to using it and not even have to try to memorize it. Yeah. But could be useful, but again, you don't have to memorize these values. Yeah. Okay, we'll go through this example here. We'll do a couple. We'll do a couple. Okay, so we are calculating the number of joules of heat required to raise the temperature of 123 grams of water from 14.7 degrees Celsius to 31.1. So we know mass of water, we know the delta T, change in temperature. We can find the specific heat of liquid water, and then we can calculate the amount of joules required. So we'll use our equation Q equals mc delta T. This is one of the equations that's on your equation sheet that you have for your exams. So Q equals mc delta T. M is mass. We're provided 123 grams of water. The specific heat of water, this is the one I told you could be useful to memorize. We're already using it. 4.184, if you need to look at our table, make sure you're looking at the correct phase. It's another thing I forgot to mention. Different phases of compounds can have different specific heats. So liquid water has a much higher specific heat than water vapor or ice. So 4.184 for the specific heat of water in units of joules per gram degree Celsius. And then delta T, I'll write the equation up here, is final temperature minus initial temperature. So if we're raising the temperature of water from 14.7 to 31.1 degrees Celsius, the final temperature is 31.1 degrees Celsius, and the initial is 14.7. So if we work through the math, calculating the change in temperature first, so 31.1 minus 14.7, and then multiplying by the specific heat and by the mass, Q is equal to 8,440 joules. So that is the amount of heat required to increase the temperature of 123 grams of water from 14.7 degrees Celsius to 31.1. Now we're increasing the temperature of the water. That means the water is absorbing heat energy to increase in temperature. So our Q should be positive. That checks out with this equation. Our Q value is positive. If we were decreasing the temperature of water, then we would expect our Q value to be negative. So we can always think back and make sure that our final value makes sense given the situation. Okay, let's go to the next question. I'll give you all a minute or two to start working on this, and then we'll go through it together. So calculate the final temperature after 1,485 joules of energy is added to 16.7 grams of water at 23.4. So in this scenario, you know how much energy is added. You know the mass of the water and the initial temperature of the water. You're trying to find the final temperature.
Usually, sorry, no, that's okay. Usually, I make mistakes a lot of times like that. And then you yeah. Oh. Yeah. But you don't want to round to the very.
Yeah. You would have made the 0. You would have lost.
Sometimes it'll be more. Okay, we'll get started going through this together now. Okay, so we're calculating temperature change. We are using Q equals MC delta T. We have Q, we have mass, we have specific heat, and then we're looking for the final temperature. So we'll rearrange this equation. At least that's how I'll do it. If you like to write in all of the values here and then solve for the variable, that's fine. But I'm going to rearrange this so that we have delta T is equal to Q over mass times specific heat. And then once we find delta T, we'll find the final temperature. So energy is being added. So our Q value is positive 1485 joules. Our mass is 16.7 grams. And our specific heat is 4.184 joules per gram degree Celsius. Now I had a good question. How do you know what specific heat to use if you're working with water? So some questions will say you're heating water vapor or you're decreasing the temperature of ice or solid water. But if they're not specifying, you can think about where water exists as a liquid in terms of temperature. So the melting point of water is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. So as long as you're between 0 and 100 degrees, then you're working with liquid water. If it's above 100 degrees, that's water vapor, gaseous water. If it's below 0 degrees Celsius, that's solid water or ice. So if we solve this fraction, we simplify the fraction, we have a delta T value of 21.3 degrees Celsius. So delta T, which is T final minus T initial. So we don't know T final, but we know initial temperature is 23.4. So this is all equal to delta T, which is 21.3 degrees Celsius. So then if we add 23.4 to both sides, we have final temperature is equal to 44.7 degrees Celsius. So again, we can think back. We're adding energy to a water sample. The final temperature should be higher than the initial temperature. And this works out. We have a higher temperature than the initial.
Yes.
So if the water is at 100 or higher than 100?
Good question. We'll talk a lot about that in Gen Chem 2. At 100 degrees, it can exist as both water and water vapor. So it will, if it says 100 degrees, it'll specify if we're working with water or water vapor. And I don't think we do any phase changes this semester. We will next semester. Other questions? Okay, well, we're gonna try to do 2 more. This first one is a little bit more straightforward. So we're calculating temperature change from adding 250 joules of thermal energy to first 0.75 moles of mercury. So the only difference here is that we're working in moles of mercury, so we should have the molar heat capacity. So we'll use Q equals NC delta T. The molar heat capacity of mercury is 27.983 joules per mole degree Celsius. They're giving us Q, so it says we're adding 250 joules. So the system is gaining 250 joules, so Q is positive. And let's see, we're calculating temperature change, so we're calculating delta T. So we'll rearrange the equation. Delta T is equal to Q divided by moles times molar heat capacity. So 250 joules for Q divided by number of moles, 0.75, times molar heat capacity, so if we simplify this fraction, we have delta T as 11.91 degrees Celsius. Now, I'm not going to go through part B. I'll give you what the final answer is, so the delta T for this. But before I give this to you all, first we calculated the change in temperature for adding 250 joules to 0.75 moles of mercury. Now, in part B, we're calculating the change in temperature. We're adding 250 joules to 0.35 moles of mercury. Would you expect the delta, don't tell me, but would you expect the delta T for part B to be larger or smaller than the delta T for part A? Think about it and then talk to someone around you. See how what you're thinking. Okay, what do we think for part B? A larger or smaller delta T?
Larger.
Larger? Why is it larger? Or what are you thinking about when you're thinking?
You're adding the same energy to smaller amounts.
We're adding the same amount of energy to a smaller amount of the substance. Yes, we're adding 250 joules, same amount of energy, but here we only have 0.35 moles as opposed to 0.75. So if we have fewer moles of the substance, fewer amount of the substance, but adding the same amount of heat, that smaller amount will be able to increase in temperature by a larger amount, so a larger delta T. This delta T is 25.53 degrees Celsius. So you might try working through this on your own.
The next one, I will also give you this. We're looking for Q. This is, I'm going to give this to you in kilojoules. So be careful about units when you calculate this. And then the one that I wanted to go through today, which we won't have enough time, but we'll set up the idea, and we'll actually work through this at the beginning of class on Friday. In this example, we have a mass of some solid that's transferred from boiling water. So it starts at the temperature of boiling water, in this case 99.8 degrees Celsius. And then it's transferred to a certain amount of cooler water that starts at 22.5 degrees Celsius. So the temperature of the cooler water raises to 24.3. So when you're taking that hot solid and putting it into the cool water, the temperature, the heat flow from the solid to the water increases the water temperature. Now we're going to use this information to calculate the specific heat of the solid. So we'll use that Q water. So heat absorbed by the water is equal to the heat lost by the solid. If you want to try that out before Friday, feel free. There's plenty of these on your Achieve homework. But we'll start here on Friday. The extra Halloween candy left over, some of that is in my office, so if that gets you to come to office hours, just know there's candy.